Aujourd'hui, nous avons une rencontre qui est à l'heure de notre colloquium habituel des sciences mathématiques du Québec. Mais c'est une occasion exceptionnelle parce que aujourd'hui, c'est une conférence pour le prix de la Société de statistique du Canada et du CRM. Le prix est accordé à un statisticien au cours des 15 années suivant son doctorat, pour souligner des travaux de recherche d'exception en statistique. This prize has already a distinguished history of almost 25 years. And this year, it is awarded to Professor Pengfei Li from the University of Waterloo. Professor Li has obtained his PhD in 2008 at the University of Waterloo. Is this correct? Is it 8 or 7?
7, end of the 2007.
Okay, sorry about this. I had a doubt. So he is internationally renowned scholar for research on finite mixture models, empirical likelihood, density ratio models, and other topics. And he will speak today on the full, as it's written on his nice slide, on the full likelihood inference for abundance from capture-recapture data, semiparametric efficiency, and EM algorithm. So Professor Li, please go ahead.
So good afternoon, everyone. Thank you for coming to this seminar. Also, I'd like to thank Erica for inviting me to be here. It's a really great honor for me to receive the prize and give a talk today. So today I'm going to talk about empirical likelihood-based inference for the abundance from the capture-recapture data. In this talk, I will cover the method, the theory behind the method, and then the numerical algorithm for the implementation. That's the EM algorithm. So this is a joint work with my colleague, my collaborators, Dr. Yukun Liu, and the student we co-supervised, and Dr. Jin Qin from NIH. Now here's the brief outline. So in the first part, I will introduce capture-recapture experiment, abundance, and then we provide a literature review on the existing method. After that, then we introduce our proposed method, empirical likelihood method, and present some theory behind it. In the third part, we discuss how to do the numerical implementation. After that, then some simulation study, and then a very quick summary. Now, let me start with the introduction and abundance and capture-recapture experiment. In many fields such as biology, ecology, and reliability study, it's important to know that the abundance of the species, the size of the closed population, or the number of the defects in the system. In some situation, we may not be able to count all possible individuals in the population of interest. If that's the case, then capture-recapture experiments are widely used to collect the data. So in this experiment, individuals from the population of the interest are first captured, and then marked, and then released. After a certain time, after the individuals has been mixed with others, then another sample is going to be taken. We may repeat the whole process several times to get more than 2 samples. Capture-recapture method was originally proposed in biology and ecology. After sometimes it has been widely used in many other areas. The following just 2 examples. The first example is June 2006. They used the capture-recapture method to estimate the hidden software errors for AT&T 5E switch. In this experiment, 6 reviews are asked to detect the errors in the system. The second example is about the COVID-19 infection detection. Born in 2020, they used the capture-recapture method to estimate undetected infection of the COVID-19 individuals. I believe that he has several follow-up papers after the first one. If you're interested in more examples, we can find them in these 3 books about the capture-recapture experiment. Okay, so that's the introduction about abundance and capture-recapture experiment. Now, In this talk, our interest is to consider statistical inference for the abundance of the closed population based on the capture-recapture data. One key assumption is that the population must be close to both the immigration and emigration during the study period. This just means that the size of the population does not change in the study period. I must agree that or admit that this assumption is reasonable only when the starting period is not too long, it's small. So if the starting period is long, then this assumption may not be reasonable. But in this talk, we just assume that this assumption is correct or satisfied. Now, the following are some details for the example that I will use throughout the talk, and also this example motivate our work. This example is about mountain pygmy possum. This is Australia possum. Now, here's a picture for these tiny animals. This possum was thought to have become extinct until 1966. After 1966, then there has been a continuous interest from the zoologists. They are interested in how many are there. Now, the capture-recapture experiment for this example was conducted at the mountain Hotham in the soil field of Victoria over 5 consecutive nights. They just say that for this experiment, 5 samples has been taken. For each captured animals, the body weight information was measured, and then this information is used as a covariate. So this is our covariate. Now for this data set, 40 possum were captured at least once over the 5 samples. And the interest is what's the abundance here. Now I came to the data structure and then connect with the example we have. Throughout of this talk, I will use the small k, lowercase k to denote the number of the samples from the closed population. And then we use the lowercase n to denote number of the individuals observed in the k samples. So this is the number of the individuals which has been captured at least once. We use x to denote individuals covariate information. We use d, this is the k by 1 vector to denote the capture history of the individual. For the GS component, the GS indicator variable dj equal to 1 if the individual is captured in the GS sample. dj equal to 0, that means it's not captured in the GS sample. So dj, the GS component, is indicator variable. Our interest is the capital N, is the abundance of the closed population. So this is unknown parameter, it does not change during the study period. If we collect with the data set we have, the small k is equal to 5, we have 5 samples. Small n is equal to 43. 43 animals has been captured at least once, and x denote the body weight. Here's one example for the capture history. For the data set we have, if the capture history is 1, 0, 1, 0, 0, it just means that the animal has been captured in the first night, the third night, but not the second, fourth, and fifth night. So that's just some notation for the data set we have. Now, the following table summarized the information for the uncaptured individuals. Basically, for the ice captured individual, what we observed is the covariate xi. We have the capture history, which is k by 1 vector. Every element will be an indicator variable. Based on this capture history, we can also calculate the summation of the DI. And the notation, I will use the DI plus. So for each captured individual DI plus, the total number of times that the individual has been captured should be greater than 0. If it's equal to 0, then we cannot capture this individual. So DI plus just has to be greater than 0 for the data we have. Now, our interest, based on the data from this table, we are going to make an inference on capital N. So that's our inference problem. I would like to emphasize that the support of this capital N is go from small n to positive infinity. Small n is our data, so it's the number of the individual has been captured at least once. So this is the data. That means the support depends on data, so the inference problem is a non-regular problem. Okay, so this place I finished the data we have, the data structure we have. Now we move to the model structure. We are going to follow Huggins and Alho's semiparametric model. The first paper is in biometric and the second one is in biometrics. The model has three components. The first component on the C side, the probability of the capture on the GS sample is modeled by a logistic regression model. So basically that's for DJ. So the probability of DJ equal to 1 given the covariate is a logistic regression. Now in this formula, Qx is the basis function. This part is given in advance. That's the first component. Since G goes from 1 to K, so we are going to have K logistic regression, one for each capture indicator. Now the second component on the C side, giving capital X equal to small x, that's the covariate information, and the key capture indicator variable are assumed to be independent. Basically, the C side, the next capture does not depend on the current capture. We will discuss in the last slide, say that we have extended this to other situations. But let us assume this is correct just for simplicity. And the last component of the C side, and the covariate information for the capital N individuals are ID with unknown CDF capital Fx. For this model, we have a parametric component come from the first one. We have a line parametric component from the last component. So put together, this is a semi-parametric model. So this is the model assumption we have. We have the data, we have the model assumption. Then we discuss how we're going to make inference under this model. So based on my best knowledge, the most commonly used method under the semi-parametric model is called the conditional likelihood method. Now, conditional likelihood method has 3 steps. The basic idea has 3 steps. The first step is to obtain a point estimate for the logistic regression coefficient. We have K logistic regression model, so we have K logistic regression coefficient. We obtain the point estimate by maximizing the conditional likelihood. Now, what is conditional likelihood? Conditional likelihood is the likelihood of the small n capture history di, I from 1 to n, given that di plus greater than 0. This means that the individual has been captured at least once, and then giving the covariate information. So those are the data we can observe. This is the capture history. So this is the first step. We maximize conditional likelihood to obtain a point estimate for the logistic regression coefficient. In the second step, we are going to use the point estimate for the logistic regression model coefficient and the inverse weighting method to obtain a point estimate for the abundance. We used n tilde to do that. That's the second step. After the second step, we have the point estimate. Then we can use the Wald-type method to construct the confidence interval for the abundance based on the symptotic normality of the point estimate or log transform the point estimate. So that's the basic idea. In the next few slides, I will just provide some details for each step. The first step is how to obtain a point estimate for the logistic regression coefficient. So we start with the conditional likelihood. This is the conditional likelihood we are going to have. It's not easy, it's not difficult to derive, so I will provide some details. I will introduce some notation first. We use the beta to denote the collection of all the logistic regression model coefficient. We use the phi x beta to denote the conditional probability, condition on the covariate, the conditional probability that an individual has not been captured. So all DJ equal to 0. So this is the conditional probability. And then we would like to have a form for each term in the product. So we derive a genetic form first. We try to derive the conditional probability of the capture history D, given that DJ D plus greater than 0, so the individual has been captured at least once, and the covariate information. This step is easy to go. We only need to use the definition of the conditional probability and then the conditional idea. So we find this conditional probability can be written as the ratio of the 2 components, the 2 part. The numerator comes from the logistic regression model. So this part, D equal to small d. The denominator comes from this condition, the condition that the individual has been captured at least once. This is the probability that has not been captured. The probability of the individual has been captured at least once will come just 1 minus this 5x beta. So numerator comes from here, denominator comes from it has been captured at least once. So we have a generic formula, and then we apply this formula to each term in the product, then we get a conditional likelihood. So let's just take a product of each term. So we can find that this conditional likelihood is a function of the beta, the logistic regression coefficient. We can maximize this conditional likelihood. We get a point estimate. So that's the point estimate for beta. This finishes the first step. Now I would like to give two comments here. First comment, conditional likelihood only involve beta. So we can only get a point estimate for beta. We cannot get the point estimate for n directly because we don't have a capital N here. The second comment is that because the conditional likelihood only involve beta, so we cannot construct a likelihood ratio-based common interval based on the conditional likelihood for n. So that's the two comments. Now we come to the second step. We use the inverse weighting method to construct the point estimate for capital N. The whole idea for the inverse weighting method is very simple. It just comes from this equation. The expectation of this summation use the indicator variable technique can be written as the expectation of summation from 1 to capital N. Again, using the conditional idea, we found that this expectation is just equal to capital N. Because the expectation is equal to capital N, so naturally we can just simply replace beta by the point estimate, get rid of the expectation, and we get a point estimate of the abundance capital N. So this is the point estimate provided by the conditional likelihood. So that's the inverse weighting method. Now in the third step, we derive the asymptotic normality of the point estimate and log transform the point estimate. After that, then we derive the standard error for the point estimate, log transform point estimate. And then we construct a Wald-type constant interval based on the asymptotic normality. So these are the this is probably the most difficult part for the conditional likelihood method. So we finished the idea of the conditional likelihood, and then we would like to say that what we can get if we apply this method to the data set we have. So that's our data analysis for the conditional likelihood. So we just follow the literature. We consider the semiparametric model. We assume that the logistic regression model for the 5 samples are the same. And then the basis function for the logistic regression is 1x squared. So we have linear term, we have quadratic term. Now the point estimate based on the conditional likelihood is 59. If we use the asymptotic normality of the conditional likelihood method, a point estimate, this is the common interval, 95% common interval. So the lower bound is 33. If we based on the symptotic normality of log transform the point estimate, the 95% common interval will be 38 to 91. So the lower bound is 38. I highlight here the 2 lower bound for the 2 common interval constructed here are all lower than 43. The number of the captured, then the total number of captured individuals. Yeah, so this part, in our opinion, we can do some improvement. So motivation for our work, as we explained before, the lower limit of the all type common interval may be less than n. In our opinion, this part can be improved. Second motivation, as far as we know, the full likelihood inference under the semiparametric model has not been explored. Before we come to work on this problem, we noticed that in this biometric paper, they studied the asymptotic properties of the MLE of the abundance based on the full likelihood. So this one, they assume that fx take a parametric form. So everything is parametric for this biometric paper. After we read this paper, we feel like probably we can do something for the semi-parametric model. So those just motivate our work. Our plan is to use the empirical likelihood method to develop a full likelihood-based inference procedure. Further, we would like to use the maximum empirical likelihood method to estimate capital N, and then we would like to also to construct empirical likelihood ratio-based confidence interval for capital N. So develop the full likelihood, obtain the point estimate, and obtain the EL ratio-based confidence interval. Okay, so this finished the first part introduction. Then I move to the second part, empirical likelihood method. Let me just first review or define some notation. Remember that we use the beta to denote the collection of the k logistical regression coefficient. We use phi x beta to denote the conditional probability that the individual has not been captured given the covariant information. And then we use alpha to denote the marginal probability that the individual has not been captured. This is the conditional probability. This is a marginal probability, so we expect that there are some relationship. We can check that the marginal probability alpha is equal to the integral of the phi x beta and the conditional probability with respect to the CDF of covariant information, fx. So based on the notation we have, the unknown parameter we have is the capital N. This is our main interest. We have beta, we have alpha, we have f. So those are the collection of all unknown parameters. Now next we develop the empirical likelihood, the full likelihood. So recall that the data we have is the capture history for small n individuals. We have the covariant for the small n individuals. So we have both of them. The full likelihood of the unknown parameter will be the joint distribution of the data we have. So capture history, covariant. Now we use the conditional idea. We are going to write the full likelihood as the product of the three components. The first component, L1, is the likelihood from N. The second component is likelihood from the N covariant conditional N. Now remember that I would like to emphasize that this lowercase n is a random variable. And then the third component is the likelihood from the capture history giving small lowercase n giving the covariant information. Now the next several slides just to tell you the details about each component, each part. L1. L1, this is the first part, is the likelihood based on the lowercase n. Now recall that alpha is the probability that the individual is not captured on any of the k samples. This is the probability that the individual has not been captured. So 1 minus alpha means is the probability that the individual has been captured at least once. So based on this information, we know that the lowercase n is a Bernoulli random variable. The size parameter is capital N, and then the probability of success is 1 minus alpha. Because it's a binomial random variable, then we can easily write on the binomial likelihood. So it's just the probability mass function for binomial distribution. Now we further write capital N choose lowercase n as the ratio of the gamma function. We will discuss why we do that later. So this is the first component. Now the second component. The second component is the likelihood of the covariant information conditional on small n. Conditional on small n because for each small n individuals, it has been captured at least once. So conditional on lowercase n, it just means that each one has been captured at least once. So di plus should be greater than 0. So L2 will be the product of this conditional probability. We didn't use any kind of a fancy technique. We just use the Bayes formula. So use the standard Bayes formula, and then we derive a form for each term in the product. Very simple derivation here. So after we derive every single term in the product, then we get the second component of the empirical likelihood, L2. So that's the second component. The third component, that's the likelihood of the capture history, given that small n, lowercase n, given the covariant information. Again, following the same logic, condition on lowercase n just means that this individual has been captured at least once. So di plus is greater than 0. then it becomes the product of the conditional probability here. This is just the conditional likelihood that we have discussed before. Because we have the form for the conditional likelihood, we just copy and paste to here, then we get a third component. So up to here, we have all the three components for the full likelihood, L1, L2, and L3. Now, before I move forward, I would like to emphasize conditional likelihood indeed is just one component of the full likelihood. So this finished all three components. We take the product, and then we get a full likelihood. That's our full likelihood. Now, I would like to provide two comments here. The first comment is about this gamma function. It's related to the gamma function. So in our theoretical treatment or numerical treatment, we are going to treat this capital N as continuous. This technique indeed has been implemented in this biometric paper. We just follow theirs. There are two reasons for doing this. First, the likelihood function makes sense for any continuous capital N greater or equal to small n. So this part for continuous capital N is still well defined. The second reason is that asymptotically there is a negligible error for doing this. So we are going to just treat capital N as continuous and use the gamma function here. The second comment is that for the full likelihood, we have a line parametric component, the dfx. So we are going to use the empirical likelihood method to deal with this dfx. Now we introduce the empirical likelihood here. Now we just follow the empirical likelihood principle. We are going to model capital Fx on the covariate CDF as the discrete CDF. And the possible value for this discrete CDF will be the observed xi. And then the jump probability at observed xi will be pi. So basically dfxi will be pi. After that, then we just plug in this formula pi equal to dfxi to our previous full likelihood. And we take a log on the full likelihood, and then we drop some terms which does not involve the unknown parameter, then we get log of the empirical likelihood. So we plug in pi equal to dfxi. We take a log for the full likelihood. We just get rid of some terms do not depend on unknown parameter. Then we get a log of the empirical likelihood. Now, this is the log of the empirical likelihood. And then we would like to emphasize that the support pi should satisfy some constraint. The first two constraints just ensure that our fx is a CDF, because fx is a CDF of the covariant information. The third, we have a third constraint. The third constraint comes from this relationship, marginal probability alpha and the conditional probability phi x beta. They have a relationship here. This relationship implies the third constraint. So we have the likelihood, we have the constraint, and then we can just simply define the point estimate confidence interval based on the likelihood. So with the log of the empirical likelihood, we first define the profile likelihood of the capital N. This is the maximum of the log of the empirical likelihood with respect to beta, alpha, and m. We let capital N fixed because this is our interest. We first define the profile likelihood of the capital N. Once we have the profile likelihood of the capital N, we can maximize the profile likelihood. Then we get the point estimate of the capital N. So we maximize the profile likelihood, and we get a point estimate. We can also define the empirical likelihood ratio. We call it EL ratio function of the capital N. 2 times the maximum of the profile likelihood minus the profile likelihood. So we have the point estimate. We have the EL ratio function of the capital N. The following are just some result that a key result we obtained in our first paper. We use capital N0 to denote the true value of the capital N. And when the capital N0 goes to infinity, we show that capital N hat, log capital N hat has the asymptotic normality, and the EL ratio statistic at the true value convert in distribution to chi-square 1 distribution. We also show that the capital N hat is semi-parametrically efficient It just means that asymptotically, we cannot improve on the point estimate anymore. Now, we have also considered a special case that all the logistical regression coefficients are the same for the K logistical regression models. The results are similar. This place, I would like to discuss how to construct the confidence interval based on the EL ratio statistic. The limiting distribution of this guy is chi-square 1, so we can construct EL ratio based confidence interval in the following I3 here. So we just put all the capital N together such that the EL ratio function is smaller than or equal to 1 minus A quantile of the chi-square 1 distribution. So 95% quantile of that will be 3.84. So that's the EL ratio based confidence interval. I have two comments here. The first comment is that the empirical likelihood function is 0, or the empirical likelihood ratio function is infinity when capital N is smaller than small n. So this automatically implies that the lower limit of the proposed confidence interval is going to be at least small n. So that's the first comment. The second comment is that after our first paper, our student has extended the empirical likelihood method for continuous time capture-recapture data, capture-recapture data with missing covariate, and also the one-inflated capture-recapture data. The results are very similar, so I will still concentrate on the discrete time capture-recapture data we consider in this talk. Okay, so now I finished the empirical likelihood method and the theory behind the empirical likelihood method. We move to the third part, that's the numerical implementation. To use the empirical likelihood method, we need to know how to evaluate the profile likelihood PLN here. Now, we propose just recently, we figured out that we can use the EM algorithm to do the numerical implementation. Now, why does the EM algorithm work here? The reason is as follows. Given capital N, profile likelihood assume that capital N is given. So given capital N, the data structure looks as follows. For the first lowercase n individuals, we observe the covariate. We know their capture history. We know the total number of times that the individual has been captured. So we know everything for the first lowercase n individual. For the next capital N minus small n individuals, we don't observe their covariate because they are not captured. But we know that their capture history, every place should be 0 because they are not captured. We know the total number of times that they have been captured. So basically, it just means that we have some complete data, we have some missing data. So that's the summary here. Given capital N, the covariates are missing for the n+1 individual to nth individual. This is just a missing data problem. Indeed, it's a missing, not a random missing data problem. So EM algorithm can be naturally applied because this one is mainly for the EM for the missing data. So we discuss how are we going to use the EM algorithm to calculate the profile likelihood. Just to recall that the profile likelihood is the maximum of log of the empirical likelihood given beta, alpha, and f. So capital N is fixed. So we now move to the EM algorithm framework. We first discuss what is observed, what is missing. So we have the complete, this is observed data. We have covariate information for the first n individual. We have the capture history for all the capital N individual. The given capital N, the missing data will be in the covariate information for n+1 individual to capital N individual. Okay, so this is the first step. And then we collect with our method, empirical likelihood method. Recall that empirical likelihood method just a model the covariate distribution as a discrete CDF. The possible values of the discrete CDF will be the observed covariate x1 to x lowercase n. This just means that xj must be equal to 1 of the xi, I from 1 to lowercase n. So equivalently, missing data can be written as the collection of the indicated variables. So indicated variable of xj is equal to 1 of the xi. This is because our modeling strategy here. Okay, so this is a observe the data, missing data, and then we come to the EM algorithm, standard procedure of the EM algorithm. So we first write down the log of the complete likelihood of the beta, alpha, and F. Capital N is given here. So based on the data we have, then we have the joint distribution of the DI, the capture history, and the covariate. We just write as a product of the two terms using the conditional idea. The first summation is for the first n individuals, so we have completed data. The next summation is for the data we have missing data. So we have some missing component. This part is the idea is similar, still the joint distribution between D and X. We have a summation here, just we don't know that which XJ, what is the value of the XJ. It must be equal to 1 for Xi, so we have a summation I from 1 to N. So this is a general idea of writing down the complete likelihood, the log of the complete likelihood. The following are just some details for each component inside the complete likelihood. This probability of capital X equals to lowercase xi, this part comes from the modeling of fx, so the empirical likelihood method principle. The second conditional probability here, this is from the logistical regression model. We have clean logistical regression model, so we just apply it here. The last one, probability of D equal to 0 means that the individual has not been captured. So this is just our notation we introduced before, by xi beta. So this is the complete log of the complete likelihood. Those are just some details for the log of the complete likelihood. Now, after we write down the log of the complete likelihood, we take the expectation of the log of the complete likelihood, given the observed data and given the current value of the unknown parameter. So that's the E step. Now we move to E step. When we do this part, we take the expectation. We find that one of the key steps is just to calculate the expectation of this conditional the expectation of this indicated random variable, given the observed data, given the current value of unknown parameter. And we find that Bayes formula can be used to derive this conditional expectation here. So again, we just need to use the Bayes formula to derive a formula here, and then plug in the current value applied to this place. So this will finish the E step. So we take the expectation on the log of the complete likelihood. After we take the expectation, and then we move to the M step, we find that the Q function, which is the expectation of log of the complete likelihood given the observed data, given the current value of the unknown parameter. This Q function can be written as the summation of the two components. The first component is function of beta. The second component is a function of f. So this is a form for the beta, the function of beta. This is the form for the function of f. And we record that there is some relationship between alpha, the marginal probability alpha, and then the conditional probability of phi x beta. So that's the M step, the Q function. Now we can maximize the Q function to update the unknown parameter. So that's the next part of the M step. We update beta alpha f by maximizing the Q function. We find that we can simply maximize the first part of the Q function to update beta. And this step can be easily done by using the GLM function in R. We can maximize the second part of the Q function to update f. We find that the jump probability has a closed form updating. After we update the beta, the jump probability pi, and then we find that alpha can be updated similarly, accordingly.
So sorry, what is GLM function? GLM.
GLM is just R function GLM. So in R, there is a function called GLM. This function can be used to fit in the logistical regression.
So it is a class of functions.
Yes, it's a function, yes.
classify. What is this word GLM? What does this means?
You mean the GRM function or GRM, the meaning of GRM?
Simply, I don't know this word.
This is just a function name in R. It can be used to fit the logistical regression model. Sorry, I'm not sure if I answer your question or not. It's just the R function. It's just the R function for the numerical implementation. Should I continue or?
I think you can go ahead. Thanks, Pengfei.
Okay. So this is the M step. Just explain how to update beta, pi, and alpha. We would like to point out that the EM algorithm we proposed here has the usual property of the EM algorithm. It just means that the likelihood function does not decrease after each iteration. So that's the property we summarized here. Now we come to the simulation study. We have two components. The first part is for the point estimate, and the second part is for the counting interval. So first, we would like to compare the point estimate, the proposed point estimate with the conditional likelihood-based point estimate. The criteria will be the mean square error of the original estimate and the mean square error of the log transform estimate. And then the next thing we would like to compare is the proposed counting interval with the two Wald-type counting interval based on conditional likelihood method. The criteria will be in the coverage probability. We consider two scenarios. The first scenario, we have two covariate, one continuous, and then one discrete. The basis function we use is 1x1, x2, and the number of samples we consider is 2 and 3. So capital N0, the abundance is 200 and 400. So this place just to tell you what's the coefficient we have used for the logistical regression model. And the number of replication is 2000. The following table summarizes the result from the simulation, the first scenario simulation study. Our method is highlighted in blue. So for the point estimate, we calculate the mean square error of the original estimate, but we divided it by 1000. For the mean square error 2, we calculate the mean square error of the log transform the point estimate and then times 1000. Now, what we can say is that in all situations, the proposed point estimate has square mean square error. Now, if we move to the set block, that's the coverage probability, we can see that the coverage probability for the proposed method has accurate coverage accuracy. So it can still be improved. Our method perform much better here. The second scenario just mimic the real data example. We have one continuous covariate. The basis function we consider is 1x squared. The number of the samples we have is 2 and 8. In the real data k is equal to 5. So the two numbers we consider covers 5. 5 is between the two numbers. This is a logistical regression model coefficient, and this is number of the replication, 2000. The results are very similar to what we presented before. The mean square error for the proposed point estimate is smaller, sometimes is much smaller. The coverage probability for the proposed method performs much better in most situations. Again, I must admit that we can improve, but this is not something that I would like to discuss today. Okay, this is just a quick summary. I explained it before, so I will skip. So now we apply the full likelihood method to the real data we have. Based on the conditional, this is a result we obtained based on the conditional likelihood method. This is a point estimate 59. Based on the asymptotic normality of the conditional likelihood point estimate, the lower bound is 33. The second one, I2, is based on the asymptotic normality of the log transform the point estimate. The lower bound is 38. Based on the empirical likelihood method, the point estimate is 55, so very close to this one. And then the counting interval, the lower bound, is 45 to the upper bound is 127. So the lower bound is greater than the number of the captured individuals. So that's the real data we have. Now I just give a one-page summary about what we have done in this area. In this talk, we have discussed the empirical likelihood method for abundance based on data from capture-recapture experiment. I would like to emphasize two advantages for using the full likelihood. The first advantage is that the empirical likelihood method enables us to construct the EL ratio-based common interval for the abundance. This is not possible for conditional likelihood method. So EL method can do that. The second advantage is that we find that the empirical likelihood method gives an estimate with smaller mean square error. So this is something we have explained. We also develop an EM algorithm for the numerical implementation. And then we also extend the method to the models include individuals' behavior effect. This just means that the next capture depends on the current capture. And we also develop our package to implement all the proposed EL method. I think that's it. Thank you.
Thank you very much. That was wonderful. Do we have any questions? And if we do, please feel free to unmute. So Pengfei, maybe I'll start us off with a question, which is, I'm not sure if this one is a totally orthogonal one, but I've been doing a little bit of work lately with networks and social connections. And I know early on you made the assumption that, you know, the data are IID, but I wonder in how difficult it would be to restrict the data or loosen that assumption, because I imagine that there are, you know, sort of clumping behaviors when you're doing this sort of sampling. And I wonder if that's something that could be eased or whether that's really a very difficult extension to make.
I think it is slightly easy to do. We have made two things along this direction. And the first thing is that we are trying to model the individual's behavior effect. So basically, the capture indicator for the next one, so D2 may depend on D1, and then D3 may depend on D2 and D1. So we have done something like this, and we found that the numerical implementation and also the theory just similar. So that's the one thing we have observed. The second thing we observed is that I mentioned one work that we have done. My student has done. So we consider the one inflated capture-recapture data. It just means that if an individual has been captured once, it will not be captured anymore. So this is another model to incorporate this kind of the behavior effect. For more complicated case, we did not start yet because I find that in the past several years, I only find one student who are interested in this area. So this are the work he has done. So there are many things that we can explore.
Thank you. Simon?
So thank you. I was wondering about how scalable it is. Like I have a problem with like thousands of capture days and millions of individuals. Would it be possible to use these methods, or would it be too computationally intensive?
I didn't try such a big number. I have tried in the simulation. I have tried the capital N is equal to like 10,000. That's the maximum I have tried. It seems that the method still works well. More than that, I didn't try. Sorry, I'm not sure.
Okay, well, it might be worth trying. I'll reach out.
Yeah, sure. I will write it down here. So basically, you are saying that the capital N is going to be very big. Is that correct?
That's right.
Okay, I will try to do that, to run some small simulation to check. Sorry, go ahead.
Eric, I have a question.
Yes, please go ahead, Abbas. Thank you.
Hi, Pengfei.
Hi, Abbas.
Could you show the slide on the real data, the confidence intervals?
Okay.
I think it was.
Yeah.
So is it fair to say that the intervals are wide?
Yes. Yes.
Any comment on that?
Okay, let me move back to the result here. You can see that for the coverage probability based on the conditional likelihood method is much lower than the normal level. I guess one way is that to increase the coverage probability is to make your
Interval large.
interval wider. Otherwise, we cannot achieve like better coverage probability. So that I get that's the one thing that we have to pay for that to achieve a more accurate common interval. We have to sacrifice the length of the common interval.
So is this a consequence of the method, or it's something that you do it on purpose?
I think it's a consequence of method.
Oh,
the consequence of having a better coverage probability.
okay, thanks.
I'm not seeing any other questions. So that being the case, then we will thank you very much, Pengfei, for your time and for this really interesting talk. And most of all, congratulations on this wonderful prize. It was really well deserved.
Thank you very much, Eric. Thank you everyone for the question.